and discuss the issue. All right, so the way I'm going to structure the workshop is that I'm going to talk about AI for a bit and give you a particular example, which is pretty similar to the exercise that we are going to undertake in this workshop. In this workshop, we are, as we know, vehicles, cars, and are physically connected to each other. There's not much chemical difference, so to speak, but just the way they're arranged is different, which leads to the phenomenon of isomerism. And this question is pretty similar to that, wherein if you have an example, if we have coal, how do we understand its constituent atom, or in this case, its constituent walls, roof, etc., and generate something which is similar to it, which is diamond, with the same constituents, but arranged in a different manner. So we ended up calling the process deep isomerism. And the idea, as I've said, is to learn the implicit spatial feature or the distribution of built mass in the example model and give out iterations or variations of that. Now, there are algorithms already out there called auto-regression algorithms, which do this for images. What they do is that auto-regression algorithms read each pixel value of an example image and kind of appropriate a probability distribution of all the pixel values. And of course, the more iterations you let it run, the closer the pixel distribution probability will be to reality. And once it learns this probability distribution of pixel values for a given image, it can then generate new images which use the same constituent elements, but they look different. In other words, if we talk in terms of architecture, we're using the same kind of walls, but they're arranged in a different manner. So it's not literally the same, but it's quite similar because it's using the same constant walls. If there were two walls, then two walls would be used. But the problem was that, again, it worked in pixels. There was no direct way for us to represent 3D geometry in this particular algorithm. So we kind of had to undertake a workaround where we started to represent 3D geometry in terms of 2D images. Now, because the neural network of auto-regression was already available, our challenge was to convert the 3D geometry into corresponding image. And once auto-regression is done, convert the output images back to 3D geometry with the information of the initial set of walls and roofs and platforms, etc., etc. Just to give you an example, how can this be done? First of all, we overlay a grid or underlay a grid on the 3D geometry. Of course, the number of cells of the grid, the size of the cells of the grid, all of those are flexible. This is an illustrative example. And once the grid is underlaid, we can identify how many unique cells do we have in this geometrical system. For example, for the geometry on the left, the unique cells are on the right, which signifies something. Keep in mind that if we repeat all these unique cells in a certain manner, then this geometry would be arrived at. If we repeat them with a different percentage distribution and also at different locations, or we place them differently, in both the cases, we will not arrive at the same geometry, but there will be certain resemblance between this geometry and the other. And that is basically at the heart of this exercise. Now, once we identify the unique cells, then we kind of mark which cell has which unique identifier. For example, this bottom left is all 0 because there's no geometry over here. If you notice this wall, which goes from the left to the right all throughout, you'll find these numbers 199, 199, 199 repeated all across. Now, just as an example, for this wall, the first value is 163, whereas the second value is 199. Why is that? If you look close enough, you'll notice that the wall goes only half the way at this cell at the edge, whereas for the rest, it goes through and through, which means that the cell at the edge is different from the cells that constituent the rest of the wall. So again, we're talking about unique cells. So reduction of surface area, reduction of volume, etc. and etc. All these factors yield a different unique cell. And this image on the right is the image representation or the pixel representation of the geometry. Now, if you can start to correlate. So there are 1, 2, 3, 4, 4 walls that go through and through, 2 in each direction. And over here as well, as you can see, the dark lines go through and through. And there are 2 in number. Now, certain pixels are darker because in those pixels or in those corresponding cells, the surface area or the volume of the geometry is higher. So it's kind of all correlated. And once we feed this image of the 3D geometry into autoregressive algorithm, we start to get these variations where, as you can see in certain examples, it is able to pick the idea of continuous lines. In certain examples, it doesn't work so well. We sort of start to get this tilized patch, which of course will lead to gibberish, etc. and etc. Now, again, sticking to the same example of the 3D geometry, at the end of 1,000 iterations, the kind of output we were getting is shown in this video on the right. A lot of it is indeed gibberish because the alignment of the individual cells is not perfectly done. However, you can start to see certain patterns emerging. Certain walls are continuous. So at this point, it is able to learn that there are certain patches where the alignment of the unique cells need to be right next to each other. There cannot be a 90-degree rotation. And in certain cases, the ground level platforms start to become continuous, but yet it has holes, and all of these options could quite literally be called gibberish, even though there's a hint of promise in there. If we increase the number of iterations to 10,000 from 1,000, then we start to get absolutely clean isomers or variations. And if you count the number of walls, you'll find that the number of walls remains the same. Keep in mind, we didn't explicitly mention that there are 2 continuous walls in one direction, 2 continuous walls in the other direction. We didn't explicitly mention that wherever we have a roof, it needs to be watertight to the walls around it. We didn't mention that wherever there's a platform, or if indeed you're adding a platform, it needs to be watertight to the walls around it. None of that information was added. It learned it from the spatial distribution after the geometry was represented as an image. And then it auto-regressed new images, which were then converted into 3D geometry. And we started getting this clean, beautiful set of variations. We've just started exploration of this process, so we haven't undertaken any examples of geometries which are not orthogonal in nature. That's a whole different ball game and a whole different challenge. But while we stick to orthogonal shapes, multiple geometries could also be used as input, which would mean that multiple images would need to be generated. Each geometry would be converted to a different image, and the from the images, the pixel distributions of each of those images will be learned, and the output that we'll get will kind of be an interpolation between all of these. So if certain orthogonal aggregates have a certain specific geometrical signature and another set has a different set of signature elements, we'll kind of get output which would incorporate a bit of the both. And the aim with this process is to eventually, once we also cover non-orthogonal shapes and we get it to work with those, is to have a clickable plugin where all you need to do is to model a clean, simple, low polygonal, low density model as an example, of which you want to generate iterations or variations, and you feed that into the plugin and the rest will be computed and you'll get a whole bunch of variations as an output. So for the user who is not really well equipped with parametric software or isn't interested, because keep in mind, not everyone likes to use parametric tools, right? So if we talk about the whole community of designers, having such a one-click plugin, in my opinion, would be really beneficial for people who are not naturally inclined towards computation or not naturally inclined towards the use of parametric tools. So as I said, the trick in this case was to efficiently convert the 3D geometry into its image representation without losing information on how space is divided or how spatial feature is distributed in the 3D geometry. I mean, we couldn't just have taken a screenshot of an isometric view or a perspective view and just went ahead with it. That wouldn't give us the 3D information to take the output and stitch back a 3D model. This is the way that it can be solved, or at least one of the ways in which it can be solved, and the rest need to be explored. Right. Lastly, I would talk about the example that I briefly mentioned, which is pretty similar to the exercise that we will undertake. Before I get into that, just to clarify, because I in the Google form, I noticed that a couple of you have mentioned that you don't have much idea about the use of AI or where AI is used. So for the sake of your understanding, I want to sort of compare traditional program with neural networks or AI. And many of you must have seen this image or this ideation. In traditional programs, or let's say in Grasshopper scripts, we define the rules, the algorithm is known, whichever phenomenon or whichever process we are trying to automate is known, it's crystal clear, it's not a black box. So with someone or a bunch of people define the explicit rules in terms of coding, and then at the end you feed the data, which is basically input data, and the traditional program will give you the answers or the output. Now, answers could be a whole bunch of numbers, it could be geometry, it could be image, etc. and etc. The data form or the data type is not important. AI is used in cases where the process is not clear. We don't know how a set of input values or input data leads to a certain set of output values or output data. We don't know the process. The process is a black box. However, we have a whole lot of examples. And by examples, I mean through observation or empirical analysis, we have a whole list of input values and output values. And what AI does is that it quite literally maps how those input values can lead to certain output values, which also we feed as example, and kind of appropriates that black box space, which we, through empirical analysis, are unable to figure out or to express it in an articulate manner so that computer scientists would be able to encode it in an automated solution. Now, I'll give you an example from the architecture process. all of us, I'm pretty sure, have worked on daylight simulation at some point in our career or in our studies. This is an example of a traditional program because the complicated algorithms or the formula that go behind daylight simulation have been understood or have been arrived at through empirical analysis of the observed data within buildings, which is why when we run a simulation of daylight, we don't need example data. We just need to feed the input values. What is the geometry? Where is the finish of the geometrical parts? What is the location? And of course, what is the time and the period of simulation? And through the process or through the algorithm, which is already defined, we get a grid of lux values, which kind of tells us the daylight level of that particular space. Now, in this equation, where could AI be used? I mean, we already have the formula for daylight simulation. Of course, we're not going to use AI for that because that will be an overkill because we don't need that. What ends up happening is that no matter how close the construction is to the specifications in the drawings, there's always a certain difference. There's always a certain delta between the simulated and predicted daylight levels, predicted through different complicated software, and the actual observed daylight level at the site post-construction. There's always a certain delta. Now, we are yet to empirically understand and observe. In fact, forget about empirical detection. We are yet to, as a fraternity, compile a data set which could be used to empirically understand the correlation between the simulated value and the observed value. In the absence of that, the use of AI could be pretty useful because we don't know why or when or at which place by which amount the difference between simulated value and the observed value would be high or low. So if we end up collecting a whole bunch of observed data and the simulated predicted data of the same site or the same project, before someone takes the trouble of extracting empirical formula out of that, AI can be used to kind of appropriate this or to predict how much of delta we'll have between the simulated value and the observed value. So as a thumb rule, when we know the process, there's no point in using AI. AI is only used in the cases where we don't know the process and we need to understand, we need to predict output of new data points. Now, our workshop is about urban beauty, and we will talk about how the qualitative aspect of urban beauty can be translated into quantitative numbers. And of course, then we're going to use those numbers to train a neural network to predict the urban beauty of new cityscapes or new images. Something similar, as I've told, we've done with the idea of urban safety. And what we realized was that whenever we talk about urban safety, and this is true for urban beauty as well, whatever I'm going to say about urban safety right now will be true about urban beauty as well, except for the final result or the matrices or factors that will need to be figured out with more research. But the idea, the presenting idea would be the same. Now, what ends up happening is that whenever we talk about safety in particular, we discuss a lot of active measures, which would be increased police patrolling, a faster complaint or grievance redressal system. And then there are certain long-term plans, and rightfully so, which would include educating children in school about gender sensitivity, etc., and etc. Now, often what is overlooked is the idea, or not idea, the fact that it is urbanscape or the cityscape, which quite literally provides the canvas on which all the interactions happen. Most of the interactions are positive, some of them are neutral, and unfortunately, a certain percentage would be negative in nature. However, regardless of which kind of interaction you're having, all of those interactions, as I said, happen quite literally on the canvas that is painted by cities. And if you come to think about it, each person would feel different if, let's say, if you're dropped in the middle of a highway, how safe you'd feel would be different compared to, let's say, if you were dropped in front of a shopping mall, or you were dropped right in front of a railway station. How you perceive safety would be completely different. And something similar, of course, happens with how we look at beauty in cities as well. If you go to different parts of cities, how we perceive beauty of that particular cityscape would be different. And not only will it be different from one place to the other, but if you change the subject, instead of me, if one of you is put in the place, the kind of safety that I'll perceive, or the kind of beauty that I'll perceive, will be completely different compared to the kind of safety or beauty that you would perceive. Now, there are many different ways of dividing classes or groups of subjects. In the case of urban safety, because in India there's a lopsided violence against women, we decided to club them as men and women, and to kind of find correlation between, just by default, how unsafe women feel in cities, even if there's no negative experience, just by virtue of how you walk through the city, what could be the correlation. In terms of beauty, one could say that we could divide it between designers and non-designers. Are designers really able to predict or understand or appreciate cities the same way that non-designers do? Are we too sensitive towards beauty? Are we less sensitive towards beauty compared to non-designers? I don't know the answer to that. That could be one probable way of classifying the case of urban beauty. Now, if we talk about seeing or looking or experiencing a cityscape from a distance, as in you look towards a certain direction and you see a vista or a whole bunch of buildings, etc., and etc. Research says that there are 4 different things at play when we observe a cityscape, or when we quite literally look out of the window in a city. Number 1 is compositional segregation, which is to say that our brain automatically segregates what we're seeing into, let's say, on the left, I see built mass. On the right, I see trees. In between, up top, I see sky. And then in between, down below, I see a road with vehicles on it. So step 1 is that, not step 1, one of the processes is that no one knows if it's sequential or simultaneous. So one of the processes is that we tend to segregate the composition that we're seeing into different types. The other is, and this is more specific to objects that are moving, that are mobile, is that we tend to count the number of mobile objects. If we are right next to a road, we tend to observe how many vehicles are on the road. And even if we don't literally count, as in 1, 2, 3, 4, 5 vehicles, no, even if we don't literally do that, we kind of tend to have an understanding of, is this road full of vehicles, or does this road have 1 or 2 vehicles, so I can probably cross the road? So we kind of have that kind of computation going on in the back of our head simultaneously, or as we observe outside. And not only vehicles, it also happens with humans. When we look outside, instantaneously, without even thinking about it, we detect if a place is crowded, if a place is empty, so on and so forth. So it's not just segregating people or vehicles, but also what number of vehicles. Is it too many vehicles, too less, or what number of people are there? Is it too crowded? Is it not crowded? That kind of fine-tuned differentiation is also executed by the brain. The third is color. Pretty self-explanatory. I don't need to talk about this more. Certain finishes of buildings signify different feelings or poke different feelings in our experience. For example, if you go to an industrial belt of the town, the kind of colors you'll see would be different compared to, let's say, if you go to a part of the town which has more parks than other parts of the town. So, and color also signifies a temporal nature of cities. Brightness signifies abundance of sunlight. Gloominess, which is basically reduction of brightness, and saturation signifies probably rainy weather or cloudy weather. And of course, as you dim the colors even more, it could either signify moving towards the night, or if it's dimmed well below enough, then it literally signifies night. If you see certain patches of yellow or white with other parts being dark, then quite literally it signifies night. So color also plays not a role in how we read cityscapes, not only in terms of how we read which area it is, but also what time of the day it is. That could also play a role in how beautiful or how safe we find a place to be. The last is spatial semantics, which in simplified words means when we look at a building, which kind of building it is. Is it a marketplace? Is it a hospital? Now, given our lived experience thus far, we don't literally need to sit and think these things, right? These come naturally to us. However, this information is very crucial in terms of how we may see the cityscape, how beautiful we may find it, or how safe we may find it. For example, if we just stick to the example of buildings, let's say for religious people, arguably, if the spatial semantic tells them that here's a bunch of religious buildings, more particularly of the religion that they have faith in, probably they'll feel safer. Given the world politics, if it's of a religion that they don't look at kindly, probably they would feel unsafe. So on and so forth. There could be many examples. If someone looks outside and recognizes that it's a whole bunch of industrial buildings, also at the same time through object count notices that there aren't enough people around there, probably one may not want to venture out all alone in that part of the town. So these four in conjunction quite literally tell our brain information about a certain cityscape or a certain urban scape, and then we start to feel certain things, or we start to make calculations of how we want to navigate that space. Now, to give you examples, compositional segregation is quite literally image segmentation, where we sort of look at different patches of different object types. Now, I'll talk about image segmentation briefly later as well when we go through the script that takes care of it. Second example is object count, as I said. So not only do we sort of see which objects are people, but we also tend to count or try and have an understanding of how many people, if not in numbers, as I said, is it a lot of people or is it less number of people, etc., etc. Also keep in mind, if this human, if let's say, which I would assume is a man, but I can't be sure, of course, if this human was right in front of the camera, then the patch that would have been occupied by that human would have been much large. But in reality, in our experience, we would have known that even if this person is right in front of me, it's only one person. Just because that object or that person is occupying a whole lot of my viewing angle doesn't mean that there are a lot of people. That information is missing when you only segregate an image into constituent objects, because it only tells us the percentage of pixels belonging to that criteria. That fine tuning or that nuance can only be added with object count. And as I said, more often than not, it's used on mobile objects and not stationary objects. Of course, then there's color, depending on the input image. The dominant color that is picked from that image changes. Now, there's a whole different argument on how many colors are we to pick. Are we to pick one major color per image? Are we to pick 4 different colors per image, etc. and etc.? I'll talk about those solutions to such questions when we tomorrow, when we explicitly work with the data set and get into neural network. I'll talk about correlations, and that is when you'll be able to appreciate selection of the number of colors. Lastly, as I said, would be spatial semantics. And there are AI algorithms which, when you feed an image into, will detect what do we see in those images. For example, if you look at the first phrase of Places 365 categories, the first phrase of each of the images, you'd find that it's pretty accurate. Now, what we are going to do is that we are going to have a detailed exercise on compositional segregation, which is basically image segmentation. Along with that, I will introduce the scripts of object count and color detection, but we won't include those in our exercise or in the training of neural network. We'll only restrict the number of input to image segmentation or compositional segregation. Now, spatial semantics requires a whole different set of installations, whole different set of concepts. So we're going to skip that. We're not going to work on that. Also, one may ask, why are we skipping object count and color if we are, having a hands-on example anyway? The answer to that is, given that we are less in number, the number of images that we'll be able to rate will be limited. And with less number of rows of data, we can't increase the columns so much. We can't have 30 variables and only, let's say, 100 rows of data. As a thumb rule, for each new variable, one needs at least 30 new rows of data. And that's the bare minimum for academic purposes. That too, the bare minimum. If you talk about professional deployment, it's not 30, it could be 1 million, if not more, for each variable. Right, so to end, we have developed SAFERNAUT, which predicts the safety of cityscapes. And we used 10,000 images, and we got them rated by men and women. We are right now working hands-on with the transgender community, because of course they also need to be represented in this conversation. And what we ended up learning from the primary correlations was that the presence of sidewalk, sky, and traffic signals made people feel secure about a space. And on the other hand, the presence of motorcycles, surprisingly enough, made people feel the most unsafe. I mean, that talks a lot about the notoriety of motorcycle riders in India, or the unsafe way in which they ride their motorcycles in India. Right, so if I talk about the method, step number 1 is, of course, to collect a whole bunch of images which need to be rated by volunteers in the real world example that I'm talking about right now. In our case, we are the volunteers. Now, of course, image collection, if you have to collect 10,000 images, it would be a pain in the ass to sit and download those images one by one, right? So even that needs to be automated. And we'll have that as a hands-on exercise as well, where we'll use Flickr API to automate downloading of images based on certain search words or certain search phrases. Part number 2 would be the feature extraction or the input variables or input data, which we are going to get using the algorithm for compositional segregation, which is basically image segmentation. And I'll talk about what are the output types when we get to that. The third would be the output data collection, which is basically the crowdsourced evaluation. And as I said, we are the crowd right now. So we will be rating a whole bunch of images. The fourth step is training a neural network with the extracted features of the images. In other words, the input values and the output values, which should be the crowdsourced evaluation or the average of how safe or how beautiful an image is. And lastly, once the neural network training is done, then any new image could be used or could be uploaded into the neural network, and the subjective evaluation will be predicted. Now, the process that we're going to undertake is, of course, not restricted to safety or beauty. The moment you change what you're asking people to review in step number 3, which is crowdsourced evaluation, the process takes a whole different meaning, right? Instead of beauty or safety, if you ask someone to rate aliveness, if you ask someone to rate how traditional or how modern an image looks, that could also give different insights in how we experience the city as we go through the city. So the moment you change that phrase against which you're asking people to judge images, the nature of the process or the output of the research completely changes just by that phrase. And there are certain takeaways from the male versus female scores of safe or not. I won't get into the details, but on average, the safety score by men was 27.74% higher than the safety score by women. And in as many as 92% of the cases, this is mistyped, men's safety score was higher than women's safety score. And as I said, we're working with the trans community right now, so we'll include that here as well once we're done. So what's going to happen is that, again, just the way it happened with safety scores and beauty scores as well, if someone does end up undertaking the research in a large scale, for each design proposal, each spot would have a different beauty sensation, will have a different beauty score. And not just that, when you're collecting data or when you're getting images rated, if you add a field for city, which city does that person live in? If you add a field of profession, if you add a field of age, then for each of those fields, you'll have different kind of beauty score, which is pretty obvious. But the moment you add a new field or the moment you add a new column in the process, the number of rows you need to add increases exponentially. So people tend to restrict that. So for example, if you pick any random image of a city, the average beauty score of that image in New York, or the score by people of New York, would be different. For people of London, the average beauty score would be different. For people of, let's say, New Delhi in India, the average beauty score would be different. And for people of Rio de Janeiro, it would be different compared to other cities in Brazil itself. So there's no one unique answer. There's no one unique value. How intricate or how nuanced would the output be? That would, as one can guess, depends on how intricate or how many columns or how many fields we incorporate at the data collection phase. So what is envisaged out of this process is that urban design proposals, one is that one can always run audits of cities. So if you either use Google Map to extract images of different neighborhoods with the trained neural network, you can generate audits of how safe a neighborhood is or how beautiful a neighborhood is, and for patches which are unsafe and for patches which are not labeled as beautiful, those could be separately addressed. That's use number one. That's a direct use of such a process. But the larger implication in the process of design would be that when designs of urban scale would be undertaken, when interventions would be designed or proposed, the residents of that neighborhood would be given an app and they'd be asked to, let's say, click or upload images which they find to be beautiful, or neighborhoods which they find to be beautiful, or click and upload stuff that you want to be built in your neighborhood. And at the same time, click or upload stuff that you don't want to be built in your neighborhood, that you don't find beautiful or that you don't find safe. And with that data itself, with enough number of residents of that neighborhood uploading enough such images with the tags, of course, there would be data to be crunched. And right at the beginning of the design process, the designer or the designers would have a fair amount of idea about the visual sensibilities of the people of that neighborhood. So the participatory nature of urban design or design proposal of the city level would be increased. Right now, designers tend to go ahead with 2 or 3 proposals, and then different stakeholders are invited to give their opinion, and then there's a back and forth process. But if such an app is indeed developed, and I'm pretty sure it will be eventually, it would be a departure from the top-down guideline producing method that are used by us right now. We tend to tell people what is good or what is bad in most of the cases, and that the power will quite literally go to the people. The power will literally be crowdsourced. And it makes sense because between different cities, what the people like or dislike is different. And forget different cities, even within a city, for different neighborhoods, the sensibilities of the people living there vary from one area to the other. And if we are to be true to our profession, then it would be prudent to quantify that sensibility and take that information in our design process. Right, so that kind of concludes the presentation. If you have any questions, kindly unmute yourself and we can have a discussion. First of all, I hope you guys are able to access the Google Drive folder that I've shared with you. You may have noticed that there are 2 folders at this moment, one called Colab Files, the other called Images for Ratings. The files that you see in the folder called Colab Files are basically the Google Colab files that we are going to use. Kindly download them locally, and then we're going to upload them on our individual Google Colab accounts. We're not going to connect this Google Drive folder to our corresponding accounts because there are multiple of us that connection won't happen properly. There are 4 files in the Colab files folder at the moment. Kindly download all of them. I will upload a 5th file before the beginning of our session tomorrow, which we will use to train a neural network. And I would take a 10-minute break before we resume. But before that, let me share a link with you. The way to access Flickr API is, of course, to first of all apply for the API, and I'm sharing the link with you in the chat window. Kindly go to this link. What you'll find is this is where they ask you only two questions. Number one, what is the name of your app? You could type beauty detection. What are you building? Just add one or two lines. You could copy paste the description of the workshop, or probably copy paste a couple of lines from there, except these two, and they instantaneously give you the API key and the secret key. We will need those credentials to run the script that will make Google Colab talk to the Flickr database and then extract images from the Flickr database. So kindly write these two down and get your credentials in the next 10 minutes or so, and I'll be back in exactly 10 minutes. Now I see that someone has typed a question. We are only going to use I will share the script and also demonstrate how to use object detection and how to use color detection. Spatial semantics, I will give you the link to the research paper, or I could share the paper and you'll have to look that up. Again, it's open source, it's developed by MIT. You can, once you work on Google Colab enough number of times, you can get it to work. Just number one, we don't have enough time to cover all of them. And number two, there are some 13 of us, out of which 7 are present at the moment. So we can't literally rate those many images to include those many variables in training the neural network. We can't have 20 variables and only 5 rows of data, right? So there needs to be a proportion in that as well, which is why we're not including that. But we'll go through object detection and color detection as well. But just because the number of variables need to be restricted, we'll only stick to semantic segmentation while training the neural network. Later on, you can always include more variables with the process. Right. All right. So I'll take 10 minutes break and I'll be back. See you guys. All right, let's head over to Google Colab to start with the first script, which is this one, Flickr underscore API underscore download. As I said, download them locally because we will need to upload these one by one to our Google Colab file or window. So I'm going to go to Google Colab. Okay, there are two ways to upload a file from the local disk space. One is when this pop-up window gets shown right at the beginning, you can click on upload and then choose the file that needs to be uploaded. Alternatively, just in case you've closed that window, you can go to File and click on Upload Notebook. And then choose the particular file. Now, as mentioned in the form that I had shared with you, some of you have not used Google Colab before. Let me talk about it briefly. What Google Colab does, first of all, Google Colab is built with the programming language Python. And what Colab does is that it lets us type Python code in our browser, which means that we don't need to install a software to execute Python. And secondly, Colab by default allocates free GPUs from the Google server for the script to be executed. Now, this Flickr download API is a pretty straightforward script where it gets access to the Flickr database, and then it downloads a certain set of images. But in the other scripts, since it uses AI, the execution of AI scripts would take significantly longer if they are locally executed in our laptops or in our workstations. The GPUs allocated to us through Google Colab are by default better specified than the GPUs that are available in our laptops and in our workstations. So the process becomes faster. And of course, it's also hassle-free, wherein we don't need to install another software. As far as the interface is concerned, Colab lets us write certain texts which could be considered as instructions or descriptions of what's happening. So this patch, for example, right at the top is a text, and the gray boxes on which if you hover your mouse, you'll start seeing this play button on the left. These gray boxes are pieces of code. We'll run them one by one, and the rest with white background are basically texts which either give us instructions or tell us what the next piece of code is all about. Right, so as it says, step number one is to import different libraries that would be used to download the images. And step number one, or the first piece of the code, will also connect us to the Flickr API. Now, one of the conventions of writing neat code is to add certain comments as written here after the hash. When you type a hash in Python, it means that you're basically writing descriptive text and it's not an executable line of code. And as it says here, it asks us to paste our key and secret within these single quotes. I am going to go ahead and do that. And if you guys have gone to that link and put in the details, you would have received something like this as well. You'll get a string which represents the key, and you'll get another string that represents the secret. Now, again, just in case you ran into any trouble getting that generated, let me paste these for you. For the time being, you could use mine, but I would request you not to keep using them. This was the key, and this is the secret. I'm going to go to Colab and paste the two. So first goes secret, and they need to be pasted within the single quotes. Single quotes basically tell Python that this is a string, which is a data type, as we know. Without the single quotes, it would be considered as a direct input or a direct number, which will run us into errors because, of course, the string contains alphabets as well as numbers. And we've got to paste key. Right. So on pasting the key and the secret, the connection to the API would be made, but there still remains an unanswered question, which is where would the images be saved? Now, Colab doesn't have direct access to the local disk space, and it could be given access to the local disk space, but usually what we end up doing is saving the images in our corresponding Google Drive folders. So if you are running, so for example, I'm running it on this particular account, the images will be saved in the corresponding Google Drive of this account. And as you are using different accounts, the images would be saved in those corresponding Google Drive folders. Colab would also need permission to access your corresponding Google Drive folders. Even though Colab and Drive are both made by Google, for safety reasons, Google does ask us to give authentication for the use of Google Drive as well. So once we execute this piece of code, that process will also be demonstrated. The way to execute this piece of code is pretty simple. We simply click on the play button. And as it processes this piece of code, you'll see the output being displayed in a smaller window at the bottom. And for those who haven't used Colab before, you'll notice that once this piece of code is run, or rather once a piece of code is run for the first time in a Google Colab file, the top of your screen would say that it's connected. And once it says it's connected with a green tick mark, it will also show you the RAM space and disk space that have been virtually allocated to you. Now, as you can see, it says permit this notebook to access your Google Drive files. Simply click on connect to Google Drive, select the account that is being used, and then you allow permission. Right, and once the code is executed, it will tell us the last line would be, the last output line would be mounted at content slash drive, which basically means that your particular drive and the account that you clicked on in the pop-up window has been mounted or has been connected to this Colab file. Now, I'll give you guys 5 minutes to get this to work. In case anyone is facing any trouble in getting the connection done or copy pasting the key and the secret, kindly unmute yourself. Or alternatively, if it's done either through the chat window or by unmuting yourself, let me know. I'll move on to the next bit of the code. Great. I'm going to go to the next step of the code, which is basically what sort of keywords we use to search images and the number of images that Google Colab is going to go through. And those two are controlled by quite literally the first two lines of this piece of the code. In that, you could use any phrase you want. It need not be related to street. Let's say I type Los Angeles street, and for a number of results, I keep it at 100 because we're just demonstrating the process. We don't need to download 10,000 images. Nor do I think Flickr would have 10,000 images for Los Angeles. Also, in the text, it tells us that for about 100 images, it takes around 30 seconds to execute. So within the single quotes, I've changed the name to Los Angeles, and I'll let the number of results be 100. Not really worried about that, and I'll run this piece of the code. Right, so the code has been executed, and it says that out of 174 files have been saved and 26 files have been skipped. In this piece of the code, images that are portrait in orientation or images that are square, in other words, images that are not in the landscape orientation, are skipped. The reason is the code was developed to download cityscape images. And of course, when we experience a city, the way our viewing angle works is that we experience a city or experience life, so to speak, for that matter, in the landscape orientation. We don't really see in the portrait orientation or in 1:1 aspect ratio. So those files tend to be skipped. Also, certain images in Flickr are pretty low resolution. Those files are also skipped. So if you have any of those two conditions, those files would be skipped. And now if we go to our Google Drive, for example, over here, if I refresh it, then I'll find that folder has been added into Google Drive. And of course, if I double click into it, I can then see the images have been saved. which basically means you can quite literally use this codes to download images with any key phrase or any search phrase. Need not be street, need not be a city, it could be any topic. And the code automatically adds numbers to the images so that they kind of get saved in a serial order. Right. I hope this is working for you guys. All right, great, Matthias. If at all, I don't suppose one should face any trouble with this because this is a pretty straightforward execution. But if at all someone is facing any trouble, kindly let me know. I would have you share your screen and we can debug the problem in that case. All right, now for the demonstration of image segmentation and then later color detection and object detection, but primarily image segmentation to begin with. Let's just use this folder that we have saved through Flickr. Now, there are certain images that I am going to delete, which don't make sense when we talk about cityscapes from the perspective of humans. For example, I'm going to delete this because this is not only a bird's eye view, but this is also black and white. We're going to delete black and white images. We're going to delete bird's eye view images or images that are not clicked from the human perspective. Secondly, we are going to delete images which are from the nighttime. Segmentation, detection, all of these algorithms have been predominantly developed with example images of the daytime. Their accuracies take a nosedive when we get into the realm of night images. So nighttime images would be deleted. And as I said, I'm going to also delete black and white images. So take a bit of time to go through your images and delete the ones which don't satisfy those conditions. So black and white, nighttime, and images not from the regular human perspective. All right. Once you clean your folder, then we can move on to the image segmentation script and then discuss its result before we move on to the other two examples. And you may need a bit of time to clean your folder. So let me just stop sharing for 5 minutes and we'll start. All right, let's move to image segmentation. We are going to go back to our Colab window, go to File, and again go to Upload Notebook. And this time we are going to upload segmentation. Okay, there are 3 blank code cells, which I guess I forgot to delete before uploading. Kindly ignore these 3. As far as the steps are concerned, in the first piece of the code, we only need to worry about one particular line, which is the 4th line. And as you can see in the 3rd line, there's an instruction written which says replace drive path here. Now, what does this mean in particular? If I go to Google Drive, we'll see that this particular folder, of course, the name of the folder would be the same as the search phrase. For me, it was Los Angeles Street. This is nested within my drive, or this is a subfolder of my drive. Pretty similar to how these how folders in our local disk space are nested within each other in a certain hierarchy. And if we click on the search bar, we see them written with backslashes. This, for example, is D drive within research, safe or not. Similarly, for this, it would be my drive / Los Angeles Street. And that is exactly how this is written. You can see my drive. At the time of writing this file, I was using a folder called AI, which was nested within my drive. I'm going to delete those 2 and type the name of the folder that is relevant to us. Remember, the name of the folder is case sensitive. If your search phrase had all lower cases, kindly type the same. And if it had a combination, type the same combination when you change the text after the slash. And that's about it. We run this piece of the code and Colab will establish connection to that particular folder. And since this file is also getting access to Drive, it will again ask for permission to access Google Drive. Each time a new notebook, a notebook in this context is the Colab file. Each time a new Colab file wants to access your Google Drive, Colab will explicitly ask for permission. The step is the same. We click the account and then we scroll down to allow it to access the drive. So as you can imagine, the second line of the code establishes the connection to Drive, and the last line of the code establishes connection to a particular folder, which we have explicitly mentioned over here, which is, in my case, Los Angeles Street. Could be a different phrase for you. So now at this moment, the connection to a particular folder has been established within Google Drive. The next step is this piece of the code through which our Colab file is going to read the images saved in the folder. We've established the connection to the folder. Now it needs to read the images. Once the images are read, then it will execute segmentation. Let's run this piece of code. There's no change that we need to execute for this piece of code. no matter which folder you're connecting, the second piece of the code doesn't require any input, nor does the third piece of code. So basically in this Colab file, the only tinkering or editing that you need to make is the fourth line in the first piece of the code, which quite literally connects it to that particular folder. Now, once the second piece of the code has been executed, it tells us the number of files that are in the folder, and just as a safety measure, it also prints out the name of the images or the name of the files within that particular folder. This is just to make sure that the right folder has been connected. There might be cases where one may have similarly named folders, but one may have uppercase, one may have a number at the end, and you may have missed it. So this is just to make sure that you have indeed connected to the right folder. Lastly, we go to the third piece of the code, and the original file for this, the link to it is mentioned over here. When you go to this particular link, you'll notice that there's a whole lot of options. There's an option to execute image segmentation on videos as well. We don't need all those options. The idea is to simplify the codes to an extent where we can use it for the specific purpose of segmenting images, particularly cityscape images. So let me run this piece of the code as well. And I'll scroll down to show you the output as and how it gets displayed. What it will do is that it will tell you which image is being segmented at which particular moment. It'll go through the images one by one. There are about 50 odd images over here, which in my opinion is going to take around 10 minutes. So let's give it the time. And while these are being segmented, if we go back to our folder, we'll notice that the script has created a subfolder within this particular folder called segmentation. If you go to that subfolder, you'll see the segmented output being saved. Again, for our reference, just for us to see and correlate visually the original images and these images. For example, if you look at the seventh image, or the image named 007, there's a patch of sky in the middle and then few trees along the sidewalk. And if you correlate it to the seventh image, I'm pretty sure that is what you'll see. Yeah, few vehicles, few trees along the sidewalk, and there's a patch of sky in the middle. So you can kind of correlate the output where the image is displayed here, or the images saved in your folder. And let's give it some time. Yeah, took about 2 minutes for 10 images. For 50 images, it's going to take around 10 minutes. Is the execution working fine for your cases?
Yeah, in my case, it's working.
Oh, great. Wonderful.
Can I ask a question?
Sure.
So each color refers to a specific class of object, right?
Yeah.
So let's say cars, they are always this specific color on the output of this model.
Yeah.
So
Cars would be in a specific column, and all the output values would be percentage of total pixels occupied by that particular class.
Okay, can you repeat the last sentence?
Yeah. Each class will have the percentage of pixels occupied by that class in the image.
Okay.
So if
on
20%
this-
of the image has vehicles, the output will be 20. Now, the 20% may be occupied by one single car right in front of the camera, or it could be occupied by 10 different cars at a distance.
Mhm.
Segmentation basically counts the overall distribution of the class. It doesn't tell us how many are there. And that missing information is to be added using object detection.
Okay. And the objects that you are interested are listed on this Python code that we are using.
That's right. Yes. And at the end, it will also, like once it's done segmenting all the images in the original folder in Google Drive, it will also save a CSV file with all the numbers tabulated.
And what is the model that we are using? It was trained specifically on what data set?
This model was developed under the leadership of Lex Friedman, who also happens to have a pretty interesting podcast in YouTube. Yeah. This was developed, I think, if I'm not wrong, back in 2016, when self-driving vehicles were a research topic in MIT. And they clicked around 2000 images, or they sourced 2000 images and used those 2000 images to develop the AI algorithm. Now, if I conceptually speaking, let me tell you how the algorithm was developed, or what is the process of developing such an algorithm. Let me open an image and I'll talk about it. I am unable to find the ready-made picture, so let me conceptually demonstrate how it was developed using Photoshop. Okay, the process is painful. because the input data set for the algorithm was marked manually. So first of all, they decided the number of classes they wanted in accordance to or with respect to self-driving vehicles. So for example, let's talk about Sky because that's easy to distinguish. And what they ended up doing was they would manually oops. Brush. Why don't I
The
see?
thing is, I think you're using an eraser. Can you should get the brush? I don't
Oops,
know.
sorry,
I
my
think
bad.
that's the
My
problem.
bad. Yes, you're right. Right, perfect. Yeah. So they would manually, let me reduce the opacity. Yeah, they would manually mark the portion which has Sky. So they would skip this part, and I'm doing a pretty rough and shabby job. They would draw polygons to mark that. So for example, this would be Sky. And this patch as well. And this patch. And they would do the same on quite literally all the images. So you draw polylines to signify Sky. Let me do that. Let me draw polylines. So for each of the 2000 images, for the bunch of research associates that they had, the job for a whole semester was to draw this polyline and mark it as such. So that's just Sky. Then they would move on to, let's say, which is the more difficult example, humans. Let me mark them with black. Now, someone would also sit down and mark the humans. Now, as you can imagine, how do you mark the humans and to what extent of accuracy you mark the humans would be different from one person to the other. And because it was done in an institute, wasn't really as streamlined as you would expect it to be. Of course, the companies that have aced self-driving vehicles do not really have those algorithms as open source. So let's say this, and all of the classes would be marked like this. So humans here as well, and one could do the same for the people over here. And all of the classes would be marked with a different polygon. And the algorithm was trained to associate each of the polygons belonging to a certain class with the kind of pixels it was seeing in the images. The algorithm was trained to not only, of course, detect the pixels, which is pretty easy to do, but also to detect edges, as in, if you're talking about poles, and if you only restrict to poles, there's no pole here. If you only restrict to this pole over here, the algorithm was able to correlate the hatch polygon of the pole with the fact that within the image, poles are quite often represented by parallel lines. It could detect the edges. As far as humans are concerned, it could detect that the edge would be kind of circular at the top with a certain amorphous shape at the bottom, so on and so forth. So on one hand, the algorithm was automatically able to detect edges and recognize the shape of the edges. And on the other hand, which edges represent which classes, that information was fed through painstakingly labeling each of the 2000 images with such polygons. Of course, with more images, higher would have been the accuracy, but this is the latest and the most prevalent segmentation algorithm that's out there, or in other words, the easiest one that is out there. There are many others, and different algorithms have different levels of accuracy. As the entry point into the segmentation space, in my opinion, this is the best algorithm to begin with, because the number of controls are less. So you get used to the process, you get used to seeing the classes, correlating them, kind of you start to value the idea of the process, and then you train it and use that to train a neural network. You get through that process a couple of times before you move on to more complicated algorithms for segmentation.
Cool, thank you.
Yes, if so, this algorithm was developed predominantly with images from Northern America, which means that most of the images do not have a lot of visual noise, which is typical of countries that are not in North America and Europe. For example, in India, we have abundance of wires hanging across the street. We have, in many places, garbage littered around the street. So the algorithm, since those were not labeled in polygons in the image data set from North America, because you don't often see those in the cities of North America. If we execute this algorithm on such images from countries where we see that, the accuracy will obviously reduce, because inherently the algorithm is not trained to detect those edges and correlate them to a specific polygon related to, let's say, garbage or related to wires. In that case, it will appropriate it to the closest neighboring class, which basically means that one of the 20 classes would have additional pixel percentage assigned to it, just because the algorithm doesn't know how to distinguish classes that have not been included in the image dataset from North America. So yeah, if we have to develop it from scratch, we need to label all of it. And again, an easy example to start that process is by using an algorithm called Pix2Pix. There was this thesis in Harvard GSD by Stanislas, not too sure how to pronounce his second name, by Stanislas, who had used Pix2Pix to automate generation of floor plans. Yes, yeah, I'm again, sorry, Stanislas is his second name. I'm not too sure how to pronounce his first name. Anyway, you can Google his name and Pix2Pix, and you'll be able to connect the dots on how to train new models or images. Yes, there would be certain cases. I'm pretty sure it has to do something to do with the wheels. Bicycles have wheels, cars have wheels, and since it's not by default trained with supermarket carts, it may end up recognizing it as a bicycle. So yes, there would be certain outlier cases which won't be recognized properly. And right now, there is a certain chunk of the discourse in the AI world, not related to architecture, but AI in general, is indeed related to how more data from non-West centric countries could be used. And it's not only a question of intent, just by virtue of where internet was developed, where internet connectivity and data storage are cheaper, just by virtue of those logistical issues, you will end up seeing that, again, the Northern Hemisphere, Western worlds have meticulously saved a lot of data, which some of the other countries haven't. So if you want to develop stuff, if you want to develop AI on, let's say, Haiti, they don't have a legacy of storing data. It's just individual people saving whatever is on their desktops. They don't have the institutional legacy of saving data. So that's a problem that the entire community is trying to crack. And which also means if Tesla comes to India, for example, I am pretty sure the self-driving mode will not be allowed in the highways of India as well, just because it's not used to detecting the signboards of India, the language of India. It's not used to detecting the kind of buildings we have in India that are built along the highway, etc., and etc. So even from a company's perspective, each time, let's talk about Tesla. From Tesla's perspective, each time they go to a country which has a completely different visual palette, they would need to train their models with images and data from that particular country right from the scratch. I mean, what they've done in the US will not be applicable in India, will not be, of course, applicable in Africa as well. All right, having said that, because this run is complete, it says that feature extraction completed. And it also says that a CSV file has been created, which we'll find in this folder. The CSV file is not saved within segmentation. It's saved outside segmentation in the original folder. If I scroll down, this is the CSV file that we will come across. Now, of course, the first column tabulates the name of the image, and the rest are basically the different classes. So for example, vegetation score of 17.5 means that 17.5% of the pixels of that particular image are assigned the class vegetation. Similarly, we have sky, person, rider, car, truck, bus, etc., and etc. There's a whole bunch of classes which you can go through later. I'm not going to spend time in talking about which classes are included. And there's one class right at the end called void, which is when it cannot detect a bunch of pixels to be worthy of being included in any of these classes, then it puts them in void class. Now, I have personally never come across any image whose any percentage of pixel has been put under the void class, because it kind of tends to find the nearest matching neighbor if it is not able to explicitly detect which class it should belong to, and tends to assign those pixels to that particular class. Right, so if you notice here, there's something called human score in column G. And there's something called person score in column S. Right, and human and person, those two words are synonymous. Now, again, like I said, with less number of rows of data, because collectively 6 or 7 of us will not be able to rate as many images needed to include all of these columns. Now, as I said, the bare minimum thumb rule is for each new variable, we need 30 rows of data. Now, with around 20 variables, we would have needed 20 into 30, 600 rows of data. Keep in mind, we can't directly rate 600 images and one rating per image to actually arrive at the score. There needs to be ideally at least again, at the bare minimum, at least 3 ratings per image to kind of get a consensus on how safe or unsafe or how beautiful or not so beautiful that particular image is. We can't have one rating per image. Now, just by virtue of how many of us are present in the workshop and how many variables can be accommodated in this particular script, what I've done is the first 6 columns, basically from build score to human score, in other words, from column B to G, these do not represent the classes. The classes are actually from column H, that is road score, all the way to void score. Now, these first 6 columns are a combination of the elaborate classes. For example, human score is basically a person score plus rider score. Rider is the person driving the motorcycle. So, for example, here 5.1 plus, let me increase the size of this. 5.1 plus 0.02, that would be 5.12. And that is exactly what you'll see in human score. So that becomes 5.12. Auto score would include car, truck, tram, etc. and etc. All of those are clubbed together. Sidewalk score would include paved. Sorry, paved score would include sidewalk, and as well as there are a couple of other metal surface finishes. So those are combined in a way for us, for the sake of this exercise, to only have 6 variables, which we are going to work with. Again, with more rows of data, with more images. Let's say if this was a workshop with 100 participants, then we would have those many rows of data. Then we would have been directly using all of these classes. Right now, the first 6 represent the rest of them, the original classes, but some of them are combined to yield certain scores. For example, build score includes building score as well as wall score and fence score. These 3 are added to give us build score, and so on and so forth. So again, for the sake of demonstration, we're going to pick data from column B to column G, but later on with more rows of data, or if you are taking this up later on your own accord, then you can use the numbers from column H to the end, because those represent the true classes. From B to G are basically additions of similar classes. Right, and of course you can directly go to a particular original class, look at the percentage value, go back to the image it belongs to, and you can start visually correlating that the output that we've arrived at is pretty accurate. All right, so that goes image segmentation. Tomorrow, what we're going to do, tomorrow we'll have a demonstration of object detection and color detection, both of which don't take much time, 10-15 minutes each. And then we'll move on to training the neural network with this data set and the images that you would be rating between the end of today's session and the beginning of tomorrow's session. And if we have time at the end of training the neural network, then I will also briefly talk about the concept that goes behind developing a neural network, what kind of functions work in the background, what does iterations or epochs really mean, what does it signify in terms of learning the process, how do patterns get detected. I'll talk about it briefly as well. Now, what I would request you to do as far as rating is concerned, That's the, yeah. There are two particular files. First is, sorry, there's a file and a folder. First is called ratings. If you open this sheet, you'll notice that I have mentioned your names and I have mentioned the image number that you would be rating. Kindly do not download this locally, because in that case, I would have to stitch different columns belonging to different participants separately. And I don't suppose I'll have that time tomorrow within the 3-4 hour time frame that we can have. And in this folder called images for ratings, the corresponding images are saved. So for example, let's say I'm Anna, and for image number 1, I'm going to open image number 1. And the options for me go from, not for me, in the same set of options for everyone, but the options that I see are from extremely unbeautiful to extremely beautiful and everything in between. So it goes from extremely unbeautiful, very unbeautiful, unbeautiful, maybe unbeautiful, unsure, and then the other end of the spectrum. There are certain things to keep in mind. There's, of course, no correct answer. Whatever your gut feeling is, you select that particular option. If you're unsure, then you're unsure. You select that. If you find another image to be extremely unbeautiful, you select that. And if you find one to be extremely beautiful, then you select that. There's, as I said, there's no right or wrong answer. Whatever your gut feeling is, you pick that particular option. Now, I don't know how many of you would be able to do this, but if possible, it's not absolutely necessary, but if possible, if you can request a non-designer friend or a family member to take part in the process as well, then we'll be able to quantify the difference between how designers see cities in terms of beauty and how non-designers see cities in terms of beauty. If you can get your non-designer friend or family member to take part in, then that'll be then the kind of output we'll get will be really interesting to read. Again, the process is the same set of image numbers for you. You could probably have that person do it along with you, or have them seated next to you, and then go through the images one by one together. The way I do it, because I've been doing this for a while, the way I do it, and you can have your own process, I tend to park this on the left and park the image on the right, and I simply basically toggle through this as I go through my options, or as I pick the rating one by one. That, in my opinion, this is the fastest way of getting it done. Now, I realized that getting non-designers to rate within this short span of time might be difficult. So as I said, it's optional. You may skip it if you don't get time, but I would honestly request you to at least complete the designer column of ratings under your name. There are only 50 images per participant. And if we can get quite a bunch of them rated, then our data set will have enough number of rows for us to then go on and train a neural network. Without enough number of rows, the data set will be too limited. Then I would have to download a data set that is already available on the internet, something to do with housing rate or population increase, and something completely unrelated to architecture or urban design, so to speak. Or probably I'll have to use the one used for urban safety and demonstrate the rest of the process. Kindly spend some time, half an hour or an hour, to rate them. And just the way the number of images are divided for Louisa and for Matthias, there's a change of the image number as you scroll down in the midway mark. So for example, in the case of Matthias, it starts at 26, goes all the way to 50, then it starts at image number 326 and goes all the way to 350. So when you see this change of image text highlighted in yellow, kindly make sure that you've snapped out of this preview and you scroll to the image that is mentioned, and then you kind of do the same again. All right, so I guess that's about it as far as today's session is concerned. If you have any questions, please, I'm available for the next 5 or 10 minutes. And the rest 3 we're going to work on tomorrow. That is, as I said, color detection, object detection, and training a neural network from scratch.
So the neural network is going to be trained like with the image features we extracted on that CSV file. Is that it?
Yeah.
And if we use it like object detection model, we would add more lines into that CSV. Is that it?
Yeah, that's correct. Yeah. Yes. So object detection value will have a different kind of value. It will signify the number of items present. So the range will be different. The range for image segmentation will be different. So when we include a data set of inherently different range or ranges, so to speak, then we have to normalize the data as well. Which basically means if for percentage, it goes from 0 to 100, and for numbers, if the minimum is 0 and maximum is, let's say, 50, then we have to extrapolate the 0 to 50 to 0 to 100, just to give equal weightages to the different columns. Or alternatively, reduce the percentage pixels from 0 to 100 to 0 to 50, just to give. Otherwise, with different ranges, neural network can tend to give different weightages to different variables. We don't want that initial bias in the process. So as a thumb rule, certain people tend to normalize everything from 0 to 1, regardless of which range you're talking about, or 0 to 100, or whichever matrix that you want to stick to.
And after the workshop, if I want to use like this model on a data set of my city, for example, will I be able to do it?
Yeah, of course, you'll be able to do it. Yeah. But once it's trained, you will be able to do it on images of your city. But again, since the number of rows will be really limited, I would displaying the outputs will be ill-advised. We'd need more rows and more larger data set for it to hold ground, academically speaking. Thank you. All right, I suppose there are no further questions. I'm going to upload the recording in about half an hour's time within the same folder. And we'll begin at the same time tomorrow. If we need to extend it by half an hour or an hour to cover all the 3 topics, I hope that won't be a problem for any one of you. And yeah, I request you guys to, at least for the designers column, add your ratings. Then we'll be able to explicitly use those directly for our neural network training. All right, it's 2 in the night over here, so I've got to crash, and I'll see you guys tomorrow. Thank you for joining me. Have a good day. Bye-bye.
Thank you very much.